Hey, what's going on, guys? Comac again here. In this video we're going to be mastering the bit manipulation techniques within the bitboards. So as I was already mentioning within the previous video, we need up to 12 bitboards to represent every piece type for white and black pieces respectively. So I will be using this chessboard within Arena GUI in order to give a visual explanation on what in particular we're supposed to be doing within this video, and then we'll implement this using C programming language. And the very first thing to consider actually, so let's deal that this squares on the board represents the bit within the unsigned long integer if we talk in terms of C programming language data types. So the unsigned long integer is the data type that consists of up to 64 bits. So every single bit would represent here it would be represented by the square on board, or every bit represents the square on board basically. And also the empty square would be equal to 0, and if I just put a pawn somewhere, don't look at this as this was a pawn. Just I'm using this pawn just to flag that the bit on the current bit board has been set up. So if we consider let's say the bit board for white pawns, in this case in the initial position we need to set all these bits to ones, okay? And if this is the case of the white knight, we need to set bits like right over in here. For bishops we need to set them here. For rooks we need to set the bits here. For queen we need to set it here. For king we need to set it here. And what did we just do? We did provide 3 operations. So we were actually setting bit, removing bit, and the fact that we see this bit is actually known as getting bit or retrieving the bit. So these are the exact 3 operations we're supposed to be implementing in this video. And also we'll write a function called printBoard that would be able to print the binary representation of the unsigned long integer, or the bitboard, also known as the bitboard, in this 8x8 squares format. So this is kind of it. So if you're interested, buckle up and we'll start writing some code now. So I've already created this file called bitboard.c, and let me just try to open the terminal in the current working directory to be able to compile and run this stuff. And the very first thing we need here is just to import a system header called, so just say include and stdio.h, and this header is needed in order to being able to output something into the console using the printf function, which is the standard output function in C programming language. And then we need to provide the main driver, because every C program starts its execution by looking at the function called main. And as far as this is the integer function, it should return something, so let's make it return 0. And now I just want to compile and run this to make sure it kind of works. So I'm using the GCC compiler on Linux. You can use whatever compiler you want. Well, maybe not really whatever compiler you want, but I think that if you would be running this in some sort of a IDE on Windows, this should work literally the same. So but I'm a Linux enthusiast, so I really like to do everything in the command line. So GCC, and then the file name bitboard.c -o, and bitboard is the name of the binary executable produced by the compiler. And if this compiles, I just want to run my bitboard binary executable, but nothing is getting output of the screen, but at least it compiles and runs without warnings and without any issues, which is already quite pretty nice. So the very first thing to consider, we need to define the bitboard type basically, and define the bitboard type. And just for simplicity and to save some space, we can define the type called U64, which stands for unsigned long, which means that this is unsigned 64-bit long integer data type. And we will be replacing, so the processor would replace every U64 occurrence within the code with these words: unsigned lon. Okay, so from now on we can actually create a bitboard like this. So just say u64 bitboard equals to 0, and if we just try to print this to screen, so just can say bitboard and print a new line. And no, the decimal is not gonna work, so it's not it's called as lon decimal. So this is the correct format specifier now to avoid getting warnings and to print everything correctly. So like this, and also bitboard is the variable to print there. So we now should see the output of 0. Okay, perfect. So this is kind of it. And now before we will start printing our bitboard, before we start writing our bitboard function, I just want to show you the idea behind getting bits first. And as far as you'll get the idea of getting bits, getting the idea of setting bits and popping bits or removing bits would be really easy to understand. So let's consider that we have some number in binary representation. Let's say like this. So in decimal this would be equal to 1, obviously, right? So let's say like, so this is the binary representation and this is the decimal representation. So here we'll have 1, and now if we just use a bit shift operator, I'm just wondering how better to lay out this stuff here. So let's say, oh my god, and if we want to shift the bits to the left and the number of times we want to do this, so just probably specify bit shift. Okay, so if we want to shift this bit to the left, so this means to the left, say one position to the left, that it would be equal to 0, 0, 0, 0, 0, 1, 0, like this. So we've just shifted this. Okay, just probably get rid of unnecessary spaces here. And let's say we want to take the same number, but we want to shift, well, let's say up to 4 elements. Then in this case it would be, so 1, 2, 3, 4. So this would be like this. So here we've just shifted this bit left for 4 points in particular. And I will now explain why exactly this is needed. This would have been needed in order to be able to actually get whether the bit is on board and then static populate this as well. But before, we need really to understand, if not understand, then at least try to I don't know, like visually imagine how this bit shift works. And so this number would be equal to 2 because this bit is worth 1, this bit is worth 2, this bit is worth 4. Okay, this bit is worth 4, this is worth 8, and this is worth 16. So if we just print, well, if let's say the bitboard is equal to 1, okay? So here we got this bitboard equal to 1. So if we just shift the bit on 1 point, the bitboard would be equal to 2, okay? But if we do this for 4 points, it would be equal to 16, because again, like this bit is worth 16. So let's have a look how this is going to be happening. This is it. But obviously the number itself doesn't really tell you much, because visually it's not that clear. Well, if this is 16, you can still imagine like where exactly the bit is, but if that is a big number of, say, up to, I don't know, 6 digits, it's incredibly hard to realize how exactly the bits are located there, basically. So that's the reason for for representing the bits in a binary format. So I will now try to actually write a simple driver to represent a bit in a binary format in a string, and then I'll make this I mean in one line, and then I'll make this in a formatable board. So for those of you who consider this to be too easy to understand, I'm sorry for such deep explanations, but this tutorial is intended for absolute beginners in terms of like what I wanted to, some sort of tutorial I wanted to have when I was just starting learning this stuff. And unfortunately I didn't have that sort of a tutorial, and I can't see this like tutorial even now on YouTube. So let's look over the bits within the bitboard, so, or within the unsigned long integer. So let's create the integer called index equals to 0, index is less than 64, and index plus plus. And now I just want to print my, well, first, so we will be okay, let's just hard code print the 0 like this, I guess. And just to give you an idea, and a new line after, so we will see a 64. So this is the binary representation of our 64-bit integer, but obviously I'm just printing the 0 for 46 times at the moment. But this is in order to explain the get bit technique in a little bit more details. So okay, now now let's put this decimal format in here and answer the question. So we will use our bitboard. So bitboard, and we want to bitwise end our bitboard with the following expression. So I will first write this expression, and then I'll try to explain what it means. So I'm using this one, the constant of integer 1, and make sure this is the unsigned long. Otherwise, this constant would be, well, it's processor dependent stuff, but most likely it would be 32 bits long. But it doesn't matter, it won't be 64 bits long if you don't specify this unsigned long. So you need to specify this unsigned long to make sure that this constant is up to 64 bits long. And we just want to shift this on the index like this. So well, before actually doing this, now it will print the very last bit would be equal to 1. Okay, sorry. Yeah, not like that, not like this. So if this expression returns actually true, then we print 1, and otherwise we just print 0 like this. Yeah, but for some reason it prints this. So yeah, I just want to, let's say index equals 64, index more than or equals the 1, and index minus minus. Sorry, I just missed the order here. So okay, excuse me. Come on. The bits are placed in a kind of wrong format, so hold on, just did I miss something? Okay, so something I'm sorry guys. Okay, let me just get back to the initial stuff. And okay, this is 1, okay, 2, okay, so this is shifting, but I just want to print this. Yeah, this is 3, this is 4. Yeah, it all right, but it all correct, but I just want to reverse the order of this bits been printed in order to match the visual kind of left bit shift with what actually happens on the screen, because on the screen we have this like in the mirrored position. So oh my god, I just really need to mirror this this sort of a stuff here. But I'm just wondering why it doesn't work with if I just start from probably I need to start with a bit of 63 and more equals than 0. I'm not sure, but okay, hold on. So is this probably, so 1, okay, and 2, yeah, perfect. So this is exactly what so now we can visually see what's gonna happen in here. So let's consider this bitboard equals to 0, and well, let's consider it equals to 1. So the rightmost bit, well, it's this meant actually 1. So if you just try to shift I mean, like if here we say 1, shift it on this shift to the left 1 position, okay, and let's say shift like 36, I don't know, position. So it now should be, oh, I'm sorry, overflow. So yeah, in this case we actually need to specify lone 1 like this. So now we did shift, because this was better, this was greater than 32, yeah. So here we have our bit bin shifted, and this expression is something that allows us to get this bit, and if it is available we'll just print it. So now let's try to dive into this expression and separate. So obviously we're not going to be setting our bitboards like this. So instead we'll set our bitboard like, say, let's make it equal to 128, and let's see where exactly the bit is set. So you remember, like, the first bit is worth 1, the second bit is worth 2, the third bit is worth 8, 4, and the fourth bit is worth 8, then 16, 32, 64, 128. So this is the exact place where this bit should be. So but this number as a decimal, it doesn't really tell us much. It doesn't tell us much if, so it's just so we have this 128, right? And this is the binary representation of 128. But in order to print this in binary, or get where the bit is, so what we need to do, so we need to generate exactly the same number. So let me just copy this and try to show you this within the commentary section. So we need to generate exactly the same number, and then we need to actually not the only bits, so there might be bits in the random parts of this integer, because pieces can be on whatever square on the board. But we start with, so first we are defining the unsigned lone constant of 1 equals to 1, and this is how it looks like in binary. And then we're starting, so index is equal from starting from 63 to 0, but well, this is mirrored, so this is a little bit not that easy to understand of how exactly this is working, but it doesn't matter really. So the idea is that as far as the index is increasing or decreasing, doesn't matter. So we just, so every time the index changes, we are moving this 1 to the left. Okay, so we're moving this to the left, and every time we move this to the left, so this is the expression, so this is how it happens. So it's just moving to the left, and at the same time so this expression represents the current state of the number where an incremental bit shift to the left was actually made, and then we just bitwise end in this bit with this bit. Okay, so we're just making this bitwise end operation. And as you know, like how the bitwise operators work, so if we bitwise end 0 and 0, this would be 0. If we bitwise end 1 and 0, this would be 0. If we bitwise end 0 and 1, 1 and 0, 0, 0 and 1, also 0. But if at some point, so it's one day it will happen that the index of our test kind of number that we're using to test, to probe the bits in the target bit board, one day it happens that the index would be equal the index of the bit that is set in the initial bit board. So when we have this 1 and 1 and we just make this bitwise end operation, this would be equal to 1. That means that this particular expression would actually return us 1 and or true. So this expression, this is the ternary operator here I'm using. So it means like if this expression returns 1, in this case we just want to print 1 within our string, otherwise we just print in our 0. So if we will have our bits being set up in a different in a different parts of the bit board, then we kind of shift into the left, shifting, and when every time when this like structure occurs, one bitwise ended with 1 would be equal to 1. Hence, we would be printing this 1 on the screen. So I hope this is quite pretty self-explanatory at the moment. So this is how we get in our bits. So now I want to start defining our bit manipulation macros. So I just want to define get bit macro, and it would be taking two parameters, the bit board and the index like this, and it would return exactly this this part. So bit board would be bitwise ended with the unsigned lon 1 shifted on the index. So this definition, so this macro works like a function at some point. So we can pass whatever bit board and whatever index. So here we're using this constant, not the constant, this the particular bit board that we've just used. But let's say we'll define 11 more bit boards, and obviously we won't be rewriting this stuff every time, right? So we'll need to use some sort of a generalization for this purpose. For this purpose. So this is how it looks like. So we're just providing the bit board as an argument. So a particular unsigned long integer that we're supposed to be probing for bits, and the current index we need to shift our unsigned long 1 constant to fit the possible index of the given bit board. And in case if they match, so if this expression, if the bit board bitwise ended with this probing test number, if it returns true, in this case we know that the bit is available at the current given index. So that's kind of it. And now we can just replace this part with just saying like get bit, and we can just say like so we're passing our bit board here and the index like this. So now it should print, now it should give literally the same number. So I hope this is quite pretty clear. Okay, so as far as this is clear, the next thing to consider would be trying to start setting our bits. So let's try to set bits like I just did this manually here, and let's try to set bit let's try to set bit using the same technique basically. So let's say okay, so probably let's make it equal to 1 for a while. So okay, so now we have all the bits been turned off, and now let's say, so here we need to take the bitboard and we need to make it equal to bitboard, and then I want to bitwise OR it with exactly the same expression. So unsigned lon shifted to the left on the current given index. So now we do the following stuff. So if here within the get bit we were bitwise ending the bitboard and with this probing unsigned lon constant integer, and this also this didn't affect the board itself really, then right over in here we would be doing the same, but we would be using bitwise OR operator. And the difference is if we say we bitwise OR this number, let's say this is the initial number and this is the probing number. So if we bitwise end this 2 bits, that will have so 0 bitwise end with 0 would be 0, and 1 bitwise end with 0 would be 1, and 0 bitwise end with 0 would be 1 as well. So this would result a value like this in return. So this is the way how we can actually set our bits. So it's quite pretty important. Okay, and so let's actually try to set our bit, and let's specify the index of, well, let's say the index of 1 just to make it seen visually. Okay, I'm sorry, printf expected. Okay. Okay, so oh my god, excuse me. Well, oh, so yeah, we did shift one bit to the left. So initially it was yeah, I mean, just hold on a sec, I'm just wondering. Yeah, so if we bitwise end this to 0, so like literally we're not bitwise ending anything. In this case, this would be 1. So the index might be 0 as well, just to bear in mind. So if we just shift 1 bit to the left, it would be like this, and in decimal respectively this would be 2. But let's try to bitwise end this to say 36 points, and now it's right over in here. And again, have a look that the decimal representation of the bitboard doesn't really tell you much, and this is exactly how your bitboards within your chess engine might look like during the mode generation and search process. So these integers don't really tell you much, but if you have a look at them in the binary representation, it starts making perfect sense, because wherever we have our bit bin set up, that's the exact place where the piece occupies the corresponding square. So I hope this is quite pretty clear. Okay, and we can also set many bits in this sort of way. So let's set like the index of 48 as well. And now you see like we have already did this 2 bits being set up here, and the number is changing significantly here. So hope this is quite pretty clear. So let's now define the second macro, and it would be called define set bit, and the set bit would be equal to bitboard, and again, and the index, and here we say bitboard, and again, like we can also rewrite this expression in a shorter form. So we can simply say like bitboard bitwise OR equals like this, and just have a look that the result is literally the same here. So this is just a shortcut for this sort for this sort of an expression, just a shortcut in C. So we used expression like plus equals, like minus equals, but we can also do like OR equals. So here I will use this short expression, so OR equals, and unsigned lon shifted to the left on the index. Okay, so from now on we can instead of writing all this stuff every time, so let's have a look again, we can just say like set bit on a given bitboard, and we need the index of, say, I don't know, 60, 63, like this, and the leftmost bit should now be being set up there. Okay, don't forget the semicolon. So we have this leftmost bit. So let's also specify, I don't know, like 35, and we have the 35th bit being set up in this sort of an easy way. So this is how we can initialize our bitboards when we want to put the pieces of a current given bitboard to some sort of a square. Now we're observing this bitboard, obviously, regardless of what kind of particular piece it represents. It might be whatever piece. So just because this bit setting and getting doesn't really it doesn't really kind of there is no difference if we use so the bit manipulations are regardless of what kind of bitboard it is, because it's always the matter of having of dealing with an unsigned long 64-bit integer. And now the very last thing that we actually need to do here is we also need to learn how to reset the bits. So let's set a couple more bits. So let's say bitboard, and let's say 28, like this. So the method that I came up with yesterday when I was playing around with this stuff regarding removing bits, I was using the Bitwise OR operator and somewhat a complicated expression, but I'm just wondering, can I simply use this Bitwise AND like, but with the equals? So okay guys, just I'm sorry, just want to check out one little thing. So we just say the bitboard and Bitwise AND equals, so we're resetting the number, we're resetting the bit here, so updating the bitboard itself, and with this expression of unsigned long shifted to, well, let's say 28, and if I did everything correctly, it should now remove this bit. Oh, sorry. Oh yeah, that's the trick. Yeah. So 1 and 1 equals to, yeah. So this won't work like this. So the way I was actually doing this yesterday was more or less correct. So we need to say bitwise OR here like this. Okay, yeah, now it works. So let me explain what's the point here. So before we're doing this, we have this bit being set up, and in order to turn 1 into 0, if we match, so we're just doing the same. So we're doing the same, like, so let's say here we have a bit. So the target bitboard is upside, and the probing bitboard is downside. Bitboard or probing constant unsigned long integer, you just call it however you want. So in this case, yeah, obviously. So if we just make a bitwise AND operation, it would bitwise AND it would return a 1 anyway. So it's not the point really. So what bitwise operation we need here is called XOR, and the idea behind XOR that if we XOR 1 and 1, this I mean, like, if we just XOR it once, it would give us a 0, but if we XOR it again, it would be giving us 1. So, well, I guess this this is far easier to explain rather than to demonstrate rather than explaining. So if we just perform this XOR operation once, we get this result, but if we just perform this XOR operation again, we'll have this result. And obviously that's not the behavior, that's not the safe behavior here. So okay, I just want to show you one little thing. So okay, I guess so. If I just copy this code a couple of times. I just want to show you what I mean by saying this. Then have a look what's happening. So first time, for the first time we did remove this bit, and then when we XOR in the second time, this bit appears again, and when we're doing this again, it again disappears, and then it appears again. So the idea is that we need to XOR our bit only in that case if the bit is actually available there. So if there is no bit, we are not allowed to XOR it. And in order to implement this, we need to say the following stuff here. So this expression is about to happen only in case if get bit, or this expression would be equal, would return 1. So just okay, let's get back. Okay, so we'll remove it. So now we need to say get bit, and we're passing our bitboard and index of 28, the exact index we're looking for, 28. And if this returns true, in this case we're doing this, right? Otherwise I just put zeros just as a placeholder, so we're not doing anything otherwise. Now let's have a look. So this should be the same result, and from now on, if we will start making this a number of times, it should always be the same, because you see, like, it's not shifting back and forth. It remains safely kept in this state, because the bitwise ending with a 28th bit would return 0, and so that's the reason why this expression won't occur ever. So now, bearing this in mind, I just want to define the very last macro. Let's call this define pop bit, which means like remove bit, delete bit, turn off bit, pop bit, and bitboard, and index as well. So here we can actually say so get bit, bitboard, and index. So if this returns true, in this case we want to say bitboard bitwise or equals, and this unsigned long shifted on the index, and otherwise we have this 0 here. Okay, so I guess that now we can already replace this with a pop bit, and let's make it like so let's pop bit 28 on the bitboard like this. So should give literally the same result. So again, like if we don't do this, we have this bit. Now if we just pop it, no matter how many times we do this, it should be all the same results. Yeah, so it gets popped, but it's not appearing ever again there. So this is it regarding setting, getting, and popping bits. But obviously we don't really want to have this weird linear representation of our bitboard. We would really like to print this as the 8 to 8 kind of table of squares like that. And also it would be a good idea to use the mapped squares. So let's say instead of providing this numbers, it's incredibly difficult to remember like what kind of number refers to the particular specific square. So it would be easier to say like set the bit on E2, or pop the bit from, or get the bit from F4, or pop the bit okay, so I'll probably already destroy that. So pop the bit from a specific square. So that's the next thing we're supposed to be implementing basically. So let's go for that as well. Well, probably I could have make, or probably, yeah, probably let's do this in the second video, just to keep this one being dedicated to the current, to the particular topic. So yeah, I would probably, so just remove this commentaries here. Yeah, that would be the best thing, I guess. And I just want to pop bit and bitboard and 28. Okay. And also, so I just want to print this before and print this after as well. So let's have a look at the output. Oh my god. Something. Okay, what's going wrong with my pub bit? Oh, hold on a sec. Should be a 0 here. Why did it disappear? Whoa. Set bit. Oh, 36. I've done something horribly wrong with with my code by pressing Control Z too many times. Okay, so for some reason, so let's print off a new line here. Okay. Okay, perfect. So also let's make new lines here. So here we set the bits. Okay. So let me probably even specify this explicitly. So what we do here, we actually, so for those of you who would be studying this code, if anyone about to be doing like that, so set bits at indices of 36 and 28 on Bitboard. Okay, and here remove index of 28 from Bitboard. Okay, so set bits at indices 36 and 28 on Bitboard, and here they are. Okay, and here we remove the bit of the at the index of 28, and we don't have it. Okay, perfect. And the get stuff is obviously used every time we want to print these bits as in a binary format, as a binary string, basically. So this is it. Well, okay guys, so I think I should stop recording this video at this point in particular in order to avoid you getting overwhelmed by the amount of the information. And in the next video I will make use of this bit manipulation macros in order to print our bitboard in a readable, in a human readable format, like 8 to 8 squares format, where the zeros would be representing the empty squares, and just like we already did, while the ones would be representing the if the piece is actually available on board. So this is kind of the plan for the next video, and this is it from my side. I hope you've enjoyed the video and learned something interesting out of it. Thanks for watching. Until the next time, and take care.